Now we come to the section of application of Newton's laws. So we learned the three laws, and now we're going to do some problem solving based on these. So we're going to learn how to do problem solving. Okay. We're going to make some assumptions. The first assumption we're going to make is that objects behave as particles or dots through the center. Okay. So we can just consider the motion of that central point of the object. We're also going to ignore all rotation for now. So we're just going to assume that the only way the object can move is through translation in any of the X, Y, Z directions. We're going to assume that if we have any masses or which are attached to strings or ropes in order to pull them, then the mass of the rope and the string is negligible. It's just the mass of the object that we need to consider. And we're also going to assume that the tensions throughout that rope or string are constant and it's one value anywhere in the string. So we're really interested in the forces acting on the given object or object of interest, and we need to find all the external forces, sum them algebraically, and then find the acceleration for that mass using Newton's second law. So if we have a string, it's going to have a tension. The tension in different parts of the rope could be in different directions, but it has the same magnitude, so magnitude T. Okay? The rope itself has no mass, it adds no mass to the system. Okay? So we're going to find that every time we need to calculate the net external force, okay, it's easier to do if we make a free body diagram. And we'll see what those free body diagrams are. They are the diagrams of all the forces acting on our object of interest. We show that object as a dot or a point and draw all the forces in the X and Y directions here. We're just going to limit it to two directions for now. And you're going to choose a coordinate system to make it simple to find which are your X direction forces, which are the Y direction forces. And then you're going to solve in both directions using Newton's second law, okay? So if you get that free body diagram wrong, then you're going to get your net external force wrong, and all your calculations are based on that, that's going to go wrong. So it's crucial to understand the free body diagram. Let's look at this case. Here we have a crate, and it's being pulled via this rope by this person to the right, okay? So remember we said the rope is just a means of conveying the force, right? It's going to have the tension which equals the force with which this man is pulling. The crate is our object of interest. We want to know how this crate moves. So we're going to locate the center of this crate and with a dot. So this is our free body diagram down here. This dot represents the center of this object. This crate has a weight downwards, yeah? That's mg. So this is our force acting downwards due to gravity, mg. Remember we said as soon as that happens, there's going to be an equal and opposite reaction from this surface on the crate. So that's our normal reaction, right? Notice how its length exactly equals the length of the gravitational force. And it's in opposite direction. So these two forces clearly cancel out in the vertical direction. We expect no change in motion in the vertical direction. In the horizontal direction, there's this tension in the rope to the right. So there's a tension in the rope with which he's pulling, right? That's the only external force with which will cause the crate to accelerate to the right. Here we have another situation. There's a mom pushing her son in this wagon, okay? So there's several things. Let us assume you're interested in the boy in the wagon, the system of the boy in the wagon. And let's assume somewhere here is its center of mass. We're going to represent that with this red dot here, right? So we want to know all the forces on this combined system, okay? Clearly, she's pushing to the right, yeah? So we have this net force to the right. The adult is pushing. There may be some friction from the ground, which is friction is always going to be opposite to the direction of motion. So if she's pushing to the right, the friction is going to be to the left. Typically, we're going to draw friction with a lowercase f, that's convention. So it's in the opposite direction of motion. No more horizontal forces. Let's look in the vertical direction. We have the weight, combined weight of the boy in the wagon pressing down and an equal and opposite normal reaction upwards from the ground. These two, again, these two are equal and opposite, so they cancel out. This is going to cancel out with a little bit of this, so you're going to have a net resultant force till about here to the right. Okay, that net force of about this much equals m into a, where m is the mass of the boy and the wagon together, and then a is their combined acceleration, given that they move together. So this here is our free body diagram, just showing the dot and all the forces on it. Okay. So in the free body diagram, you want just the forces acting on that object of interest. You don't want to show the reaction forces, okay? Because they do not directly influence the object. So in general, our strategy for solving a problem based on Newton's law, second law, is you're going to read the problem, we're going to sketch a diagram. From there, we may need to make a separate free body diagram. Okay, we need to locate all the forces with the arrows. Then you need to label the forces, okay, with the physical quantity. Say his weight is 30 kilograms, 30 newtons, sorry, his weight is 30 newtons. You're going to mark that. His mass may be 30 kilograms, okay. You're going to draw a free body diagram for the system, and then you're going to find the net force and apply Newton's second law to both the x direction and the y direction if you have net forces in both directions. Okay, you're going to solve for the unknown. Okay, so let's do our first problem. Suppose two children push horizontally but in exactly opposite directions on a third child in the wagon. The first child exerts a force of 75 newtons, the second a force of 90 newtons, and friction is 12 newtons. And the mass of the third child plus the wagon is 23 kgs. Part A. What is the system of interest if the acceleration of the child in the wagon is to be calculated? Part B. Draw a free body diagram including all forces on the system. C. Calculate the acceleration. D. What would be the acceleration if friction were 19 newtons, so friction increased? So the first part, what is the system of interest if the acceleration of the child and wagon is to be calculated? Clearly, the child and the wagon is our system of interest, right? So we would need to take their center of mass as the central dot and find all the forces on it and draw them. So let's try to show that. So say here's our center of mass, yeah? And the first child exerts a force, let's say, of 75 newtons to the right. And the second child exerts a force of 90 newtons. So I'm going to draw that slightly longer because 90 is bigger than 75. And it's in the opposite direction. So we expect the cart to move in this direction, then my friction is going to be this way. And that frictional force is 12 newtons initially, right? And then this is if I make this my free body diagram, there's some other forces here. What is this force vertically downwards? This is going to be the weight of the boy in the wagon and an equal and opposite normal reaction, right? So this would be the free body diagram. That's part B. Part C, calculate the acceleration. Now we need the force to be able to calculate the acceleration. We know F net equals m into a. So my acceleration is going to be given by F net divided by the mass. Yeah? What is F net? So we have 90 to the left, so that means negative 90. And we have positive 75 and 12. See how I'm doing the algebraic addition. I took that negative sign because this is to the left. Yeah. So this becomes 87. Yeah. I'm going to get a negative 3 newtons as my net force to the left. Yeah. Do we know the mass of the child in the wagon? There it is. The mass of the third child plus the wagon is 23 kgs. So I have negative 3 newtons divided by 23 kgs. And that's going to give me my acceleration in meters per second squared. So you're going to put that into the calculator. You're going to get a negative value. So my acceleration is going to be in the negative direction. That means my acceleration is going to be in this direction, the same direction as my net force. Yeah.